Yes, dear students, we are going to start new topic. Alternating circuits containing one resistance and another is inductance. How a current related to the voltage applied in terms of the phase relationship and how will be the impedance. Here the combined the net resistance of this AC circuit which contains inductors and resistors known as impedance. So how to find the impedance and what will be the phase relationship between current and voltage. Let us start. So we have this is our AC circuit which contains a resistors R. This is the resistors R, inductance L, and at a particular times the alternating voltage applied this AC circuit is E0 sin omega t. At that time the voltage applied across the resistor is VR. This VR is equal to I multiplied R. At that time the current in this circuit is I and voltage across the inductors will be VL is equal to I into XL. We already know that the reactance or resistance offered by the inductors represented normally XL, and then this XL will be omega into L, and the omega has the value 2 pi f into L. And also we know that we are analyzing this AC circuit with the help of phasor diagram. In phasor diagrams we normally suppose these current and voltage as phasor vectors. Therefore vector VR, and this is current vector, voltage vector across the inductors and current through the inductors. So these will be from here to here and this will be from here to here. We already know that current and voltage in a resistors are in same phase. If this is the current vectors and this will be voltage across the resistors will be in the same phase. Likely we know that when there is only an inductor in AC circuits, if this represent along I current vectors and the voltage vectors across the inductor is ahead of the current by an angles of 90. So these are phasor representations of voltage and current. Now we have to find out what will be the current phase with respect to the alternating voltage phase. Now for it we are using these voltage and current as a vector. So suppose the net EMF which is applied E is equal to voltage across the resistors plus voltage vector across the inductors, and we also know that the current amplitude and the voltage amplitude are related by a phasor diagram. Now the phasor diagram for series LR circuit. Now the voltage amplitude across the inductor V0 L is equal to I0 into XL. The voltage amplitude across the resistors would be V0 R I0 into this one. So let us start. Suppose the net voltage, this is the net voltage with this AC source applied at a particular times. This voltage E in vector format, voltage across the resistors plus voltage across the inductor. These are the vector sum we are using. We are supposing voltage and current as a phasor vectors. Therefore, by the using of the law of the parallelograms, we can find out the current from these relations. Now let us suppose the angle formed by the EMF applied to the AC circuits is omega t with the positive direction of x-axis, and the current would have let us start. This vector represented by the voltage across the resistors VR, and we already know that here VR and I are in the same phases. Therefore, along the VR, current will also be. We already know that the VL, the voltage across the inductors, always form an angles of 90 degree in anti-clockwise directions. If this is VR, along this current would be also, and the direction of VL making anti-clockwise direction. Anti-clockwise direction, an angle of pi by 2. So therefore this represented by voltage across the inductor, and using the law of parallelograms, make a parallelogram. Yeah, this is our parallelograms. The resultant of VL, the resultant of VR and VL will be along the diagonals of these parallelograms. Therefore, we already know that if a phase angles between current and resultant EMF is phi, let us suppose this is phi, and this current making an angle with the x-axis, positive direction of x-axis in anti-clockwise direction, so would have omega t minus phi. So therefore, from here our current has a value I naught sine omega t minus phi. It means that the current lagging behind the voltage by an angles of phi. Let us show it mathematically using Pythagorean theorem. By Pythagorean theorem, we can find out the value of resultant E with the help of the vector addition. Now using the Pythagorean theorem, we have voltage amplitude E naught. This is the triangles, it makes also 90 degree here. Square of this using the Pythagorean theorem is equal to square of the base plus square of the perpendicular is equal to square of the hypotenuse. Therefore, our hypotenuse, its length would be magnitude of the AC voltage. Therefore, square of the AC voltage is equal to square of the voltage across the resistors, and similarly along this one, because this is parallel to this one, because this makes a parallelogram. In parallelogram, opposite sides are equal and parallel. Therefore, if this is VL, this is also VL. In magnitudes, its length would be V naught L whole square. We already know that E naught whole square and V naught would be I naught into R whole square plus I naught into XL whole square after taking I naught square R square plus I naught square XL square. After taking I naught square out, I would have the value R square X square L. From here, I naught square becomes E naught square divided by r square plus square of xl. Now I naught whole square comes out, E naught whole square divided by r square plus square of xl. From here the current amplitude becomes voltage amplitude divided by square of r square plus square of xl. Now this under the square root we can write this as z. This z known as the impedance. Z is the impedance of the LR circuit. Now I got the value in earlier part. Current amplitude, voltage amplitude divided by z, and this z known as the impedance, whose value is r square plus square of the inductive reactance, and the inductive reactance has the value r square plus omega l whole square. Now let us find out the phase angle phi between the voltage amplitude and the current amplitude. Now our current amplitude is I naught, it's a length, and the voltage amplitude is E naught, length of these diagonals. We know that from the trigonometry tan phi, if I use the trigonometry in this triangle, tan phi is equal to perpendicular divided by base, where perpendicular will be parallel to VL. In terms of the amplitude of the voltage across the inductor divided by amplitude voltage across the resistors. So therefore its value this one. Now it has the value I naught XL divided by I naught R. After cancellation, this value I will have XL divided by R. So the angle between current amplitude and the net EMF amplitude is phi will be found out from this. Now these angles would also be calculated from impedance triangle. Now this is our impedance triangle. The phase angles between current and voltage can be found from here. Phi, and this is resistance across the resistance R and resistance across the inductor XL. So from here tan phi is equal to XL divided by R. XL has the value omega divided by R. So this is known as the impedance triangles. This is the impedance triangle of LR circuit. This is our LR circuit, and this is the applied voltage which is variables with time t in magnitude and directions. Corresponding to this, we have calculated a current at a particular time t. That current has the value